Hi, welcome to class. Last week of school, 2020, Tuesday, June 9th. We're going to review fundamental principle of counting, and then we're going to go into probability a little bit. So the first question was a warm-up question. How many different batting orders can be made from the 9 starting players on a baseball team? So, what we have going on, if we were going to use a decision chart, would be 9 decisions. First in batting order, second in order, third in order, fourth in order, fifth person at bat, sixth person at bat, etc. Now our first decision, we have 9 starting players to choose from. Now that we have chosen one person out of 9 to bat, we can't choose that person anymore. So now we only have 8 people to choose from. The third person in the batting order, we have 7 people to choose from. And you begin to very quickly see where this is going. This is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Also known as 9 factorial. Now, if you knew that this was a permutation without repetition, and you knew that the number of decisions we needed to make, k, was 9, and the number of people to fill those slots, n, was 9, so you knew that k equaled n, then you already knew that the formula we needed was n factorial, which is 9 factorial, which is 362,880. Sometimes using a decision chart like this is the best way to figure out, even if it's too big to finish the decision chart, it's a good way to figure out what formula to use. Okay, so we're going to review ways to find sample spaces, also known as different ways to find the total number of options that we have. How many different options are there? How many different ways to count something are there? This is going to turn into our sample space for probability, but we need to review this from last week because we're a little shaky on it still. So we have tree diagram, which you can use just like the example we had last week where I can buy a flower, one of 4 different kinds, in a pot, one of 2 different colors of pots. If I were to ask them to give me a flower at random in a random pot, what are the chances I would get a tulip in a blue pot? Well, there are 8 different possibilities. A rose in a blue pot, a rose in a red pot, a tulip in a blue pot, a tulip in a red pot, and so on. And so the probability that I would get that one kind of flower in that one kind of pot would be 1 out of 8. Our sample space is 8. Likewise, we can also use decision charts, just like I showed you with the baseball. Decision charts can be used for permutations with or without repetition, and I'm even going to show you how they can be used to figure out a combination, even if it's not a permutation. We learned these 3 formulas last week for permutations. N to the power of k for permutations with repetition. N factorial when n equals k. And n factorial divided by n minus k factorial when n does not equal k for permutations without repetition. And then lastly, we learned this formula for combination where we have to add the extra k factorial to the denominator. And we'll talk a little bit more about why that is. Here's a problem just to get us thinking about permutations and combinations. Small State of Euphoria recently decided to use 3 letters for car license plates, but they decided not to use A, E, I, O, U, or Y. So if they're not using those 3 letters, that means they're using 20 different letters. They also decided to use only odd digits. So they're using 1, 3, 5, 7, or 9. So they have 5 different choices for digits. 20 different choices. N is 20 for the letters, N is 5 for the digits. So let's take a closer look. So let's start with a decision chart. This would be the first character in the 6-digit license plate. The second character in the license plate, third, fourth, fifth, and the license plate has 6 total characters. The first 3 are going to be letters. If we can repeat letters and digits, that means that we can have 1 out of 20 different choices for the first letter, and we can also have 1 out of 20 different choices for the second letter and the third letter because we can repeat our choices. Meaning, we can repeat. If we choose B for choice number 1, we could use B for choice number 2 as well. So every time we're picking a digit, we're picking a letter. We're picking a letter out of the 20 available. This is a combination, a permutation, with repetition. Now we're going to do the same thing with the digits. The last 3 characters are digits. We have 5 to choose from. We also have 5 to choose from for the 5th character and the 6th character. Okay. So we can just look at this and just put this in our calculator. 20 times 20 times 20 times 5 times 5 times 5. Or we can look at it like this. If we're repeating a permutation, that formula that we use is n to the k power. So in this case, it would be 20 to the power of 3 times 5 to the power of 3. Either way, that's 1 million different combinations available for a license plate. So what about if we're not going to repeat digits? What then? Are we still going to have 1 million different choices? Let's take a look. So we still have 6 different blanks. And we still have 3 different letters and 3 different numbers. But we're not going to repeat digits this time. So we still have 20 different choices for our first character, 20 different letters we can choose from. But say we chose B, just for an example. If we chose B, we have to take that out of the running for character number 2. Character number 2 can't be B. So now how many different choices do we have for character number 2? We only have 19 different choices. Now say we chose C for that character. Once we've chosen that character, we can't use it anymore. So now, to choose our third character, we can only use 1 out of 18 different choices. We're going to treat the digits the same way. We have 5 to choose from for the 4th character, but we only have 4 to choose from for the 5th character, and we only have 3 to choose from for the 6th character. So again, we could just straight multiply 20 times 19 times 18 times 5 times 4 times 3, and that will give you the correct answer. That will tell you the number of license plate combinations there are in this case. However, what if this were a larger problem and it would be more difficult to multiply because there would be too many decisions? In this case, starting a decision chart like this can actually help you decide what formula to use. You start to realize that what we're doing here is we're doing permutations without repetition. And n does not equal k. In this case, n equals 20 and k equals 3 for the letters, and n equals 5 and k equals 3 for the digits. So in neither case does n equal k. So we have to use the full-on formula. N factorial divided by n minus k factorial, which is going to be 20 factorial over 17 factorial times 5 factorial divided by 2 factorial. Either way, this is going to give us 410,400 different combinations, permutations of license plates. So the question in Euphoria is, are there going to be enough license plates? What's the recommendation? Well, if the recommendation is that they have enough plates for at least 500,000 cars, then they're going to need to allow repetition. If they don't allow repetition, they only have 410,000 different ways to make a license plate, which will not cover the 500,000 cars that are in Euphoria. Now let's look at a combination. If we have 24 students, and we want to choose 3 students out of that bunch to play basketball with. Okay. Even with a decision chart, we can do a combination. We have 24 different choices for the first one. Now, our second one's going to be different than the first one. There's not going to be a repetition. So 23 and then 22 different choices for those decisions. However, we have to keep in mind that if I choose Barney, Sally, and Tom to play basketball with, we don't really care about the order. If we picked Barney, Tom, and Sally, why, that would be the same thing for our purposes. We're still playing basketball with those 3 people. What about Sally, Tom, and Barney? What about Sally, Barney, and Tom? Okay, there are actually 6 different permutations of those 3 people. Okay, 6 different permutations, which means we're going to have to multiply 24 times 23 times 22, and then we're going to have to divide by 6 to get rid of all of those duplicates. This is why we use the combination formula, n factorial divided by n minus k factorial, k factorial. Okay? What we're going to do is we're going to take 24 factorial and divide it by 24 minus 3, 21 factorial, and also divide by 6. But instead of 6, we're going to write 3 factorial. 3 factorial is 6. 3 factorial, 3 times 2 times 1, 6. Dividing by that 3 factorial or dividing by that 6 is how we're getting rid of all of these different 6 different permutations. Because we don't care what order we're playing basketball with them in. Okay? Either way, you're going to have 2,024 different ways to choose 3 people from those 24 students. You'll notice that when we do combinations, the number of different combinations is going to be significantly smaller than the numbers we get when we're doing permutations, where order matters. I'm going to stop this here. We're almost at the 15-minute mark, and there will be a we will do another video to continue where we left off here for class number 1.